This week, we're going to continue on with the atmosphere and its origin, composition, mainly looking at composition and structure of it, just to get you familiar with what we're dealing with this year. So, with that in mind, what is the composition and structure of the atmosphere? Well, the atmosphere covers the globe, so changes in one area might impact another area. This example they give here is the African origins of the windborne dust. In the summertime, particularly, dust comes off the Sahara Desert, and it impacts. I've seen it get visibilities as low as a quarter mile, San Juan, Puerto Rico. It comes into even areas in the Outer Banks sometimes, where visibilities will reduce to a mile in dust that's literally moved across the Atlantic Ocean and into the United States. So you can see we need a global look at the atmosphere when we're dealing with it. So weather can go from being beautiful outside, very nice, nothing happening, to, oh my, I don't want to be out there at all today. So what is the atmosphere? It's part of the Earth system. The Earth system, when you look at Earth science as a whole, you have the atmosphere, which is what we're going to deal with, the hydrosphere, which we do get some input in from. That's the water areas, the oceans, the lakes, even the pond by your house or a stream running down by your block. The geosphere, which would be more of the volcanoes, that kind of an thing that can literally impact the atmosphere. And the biosphere, which is basically plant life, plants, our lives, all of that impacts the atmosphere. The atmosphere is not really that big, really. It's a relatively thin layer of gases. And half of it literally is within 18,000 feet, little more than 3 miles up. And 99% of the mass was within 20 miles. So this is a thin layer around the Earth. Yet within that thin layer, what it does is how we can live. So the lower part of the atmosphere, the gases are all basically uniform. So what does that mean? Well, if you climb a mountain and you're up at 20,000 feet, you're still going to get 20%, almost 21% of the air is oxygen. Now, atmospheric molecules are getting less. The higher up you go, there's less and less molecules. We're going to learn why that is. So that 20% of the air still going to cause you to breathe real hard. I took a trip out west this year and went into several mountainous areas, including Rocky Mountain National Park, where I was above 13,000 feet. And I can tell you for a fact that 20% of oxygen is not nearly the same as when you're down on the ground at the sea level. So there are other particles that make up the atmosphere as well. Water vapor, mainly in the lowest 1 kilometer of the atmosphere, but it can make up all 4% of it. Carbon dioxide. It's required for life, literally, because photosynthesis, all the plants and all, but they create oxygen, which we need. Both carbon dioxide and water vapor absorb and emit infrared radiation. We're going to talk about radiation, but it's what keeps our planet habitable. Pollution. It's all over the place, and it's maybe not as bad as it used to be in some ways, and maybe worse in others. Most of it is human, man-made. The scientific method is how we study the atmosphere. I'm going to give you an example here of one that I was involved with because it affects our forecast here in the eastern part of the United States. Thunderstorms many times will be moving across the Appalachian Mountains. The biggest question that I live on the east side of the Appalachian Mountains is, will the thunderstorms continue to the east side of the Appalachian Mountains? And sometimes they do. Sometimes they weaken. Sometimes they even strengthen. Well, that was the question we asked. And we ask it working with conjunction with researchers at North Carolina State University. We wanted to know why. What is something we can pin our hopes on to make a better forecast? Which is you all. We're making that forecast for. So we formed a hypothesis that maybe there was something in the structure, and we talk about something called stability. We're going to deal with that later, that might deal with why these thunderstorms kept moving. So we posed a hypothesis. We went through and looked at it. We ran some tests on it. And we said, well, it's close, but not there yet. So we went back and refined it. And we were able to come up with a parameter that defined when these thunderstorms would actually intensify when they got on the east side of the mountains and when they would weaken. And it depended on a number in this parameter, which took into account moisture, which took into account temperatures, all different things in the atmosphere that we can measure. So we were able to come up with this, and using it, we got fairly accurate now with thunderstorms when they come to the Appalachians. Are they going to continue or are they going to die out? And by following this number and using it, using the scientific method, we were able to develop a forecast routine that significantly improved forecasts for the public. There are other ways of looking at the atmosphere, modeling chambers like Purdue's numerical models. We have tons of automated surface observing systems out there, ASOS. They're at every airport. Why they're at the airport is pilots need them. If you're going to take off in an aircraft, you want to know what the weather is where you're at or where you're landing. So you want to know that. There are cooperative networks, radiosondes, which are just basically a helium balloon being lifted into the atmosphere with a little instrument pack tied to it. They launch at about not really a whole lot of sites across the United States, but enough to give us an idea of what the upper atmosphere looked like. Remember, the atmosphere is three-dimensional. So we got that as well. And those balloons, as they go up, expand. Why do they expand? Because there's less and less air molecules around them. So the amount of molecules in the balloon keeps growing outwards. The pressure is higher in the balloon than it is around it. Eventually the balloon will burst, usually about 100,000 feet up. And here you can see the instruments used. There are radiosondes and dropsondes. Dropsondes are basically the same instrument package. They're just dropped from an aircraft. They can be dropped into various types of storms. Hurricane Hunter aircraft use them, while radiosondes go up into vertical. Remote sensing. Radars are great tools for looking at, and satellite as well, for looking at what's going on now. And here's just a temperature profile. When we talk about the atmosphere, we basically divide it as how the temperature is changing. Notice in the troposphere, temperature generally decreases. Once we hit the stratosphere, temperature generally warms. And then the mesosphere, down. Thermosphere, warming up again. So as you can see, these are the basic layers of the atmosphere, and they are really defined by temperature. The ionosphere is where you see the aurora borealis, which are beautiful things to look at when you see them. And they basically come out of the stronger the solar wind is, the bigger area of the United States or the world can see an aurora borealis. Here you can see that there. So with that, I wanted to quickly just show you. This is a satellite image today. You can see some clouds circulating right here. Clouds are out ahead of what probably is a cold front in this area here. There's a very intense low pressure well off the coast of California here. And you can see the sun. Notice it moving right along like this. And next week, that shape right there is that way. But this is just one method of taking a quick peek at what's going on in the atmosphere. And if I'm living in Ohio or West Virginia today, I'm not expecting to see a whole lot of sunshine. Now, here is a plot of the upper atmosphere called a Stuvie diagram. What does that mean? Well, it means pressure is plotted in the y-axis, and in the x-axis is temperature. That's all we've done. And we've plotted both temperature for actual temperature and moisture. And this is Minneapolis, St. Paul. You'll notice temperature got very cold, down below, well below freezing here. And then it begins to warm up to this very low level here, and then it begins to cool off. So as you can see, as you go higher in the atmosphere, temperature in the troposphere are going to cool off. Notice right here, temperatures begin to warm. This literally is the beginning of the stratosphere. The stratosphere becomes lower in the summertime, in the wintertime, because of the cold air. Cold air is denser, and so it allows the stratosphere to go down lower to closer to the surface. Whereas in the equator and all, the air is warmer, it pushes the stratosphere higher. And finally, I just wanted to give you a quick peek at a numerical model. This is an analysis generated by a numerical model. We're not going to get into much in the way of math. You're probably thanking me for that. But on this map, you can see low pressure systems here. They're in the dark color. Pressures. We have a big high up over eastern Canada right now. Low pressure over the plains. We saw all those clouds. Very strong low pressure off the west coast of the United States. Well off the west coast, actually. And the blue lines and red lines are temperatures. These temperatures are 850 millibars, which is exactly very close to 5,000 feet up in the atmosphere. It's about a mile up. So it takes away a lot of the Earth's surface influences. You can see really quite mild temperatures. Usually this time of year, 0 degrees Celsius, these are would be probably down into almost central part of the Midwest and all. Now there's some very cold air up here, closer to the Arctic, but this gives you an idea of how this is going to go into a forecast. This is an analysis, and guess what? We don't really know everything. If you drove, for example, from Beckley, West Virginia, due west to Cincinnati, Ohio, those only observations, maybe Beckley, Huntington, Charleston, nothing in Ohio until you get to Cincinnati. So there's not a lot of observations in this area. So where is the cold front? If I told you there's a cold front somewhere between Cincinnati and the West Virginia state line, where is it? Is it here? Is it here? And that is an issue that goes into every time we make a forecast, trying to determine exactly what the initial conditions are. And then if we know the initial conditions well enough to know how things are going to change. So I hope you got a little bit out of this, and please let me know if you have any questions.